I will remind you. It's a very general statement. So it appears in many different situations for many other integrable systems. So it looks like some general property, but however, there is no theorem like this. So it exists for almost every integrable systems, but finite dimensional integrable system, but it is not a theorem. So separated variables in sl₂-Gaudin model. So we started to consider the Lux operator, which is the sum of matrices like this: hi, ei, fi, minus hi, zi. These letters are generators of copies of the algebra sl₂. So our phase space is our phase space is just the direct sum of sl₂ dual space to the algebra sl₂, and here from 1 to n. So there are n copies of this linear space. It's a Poisson manifold with the Kirillov constant Suryo Poissonly structure, which we know. And so the Lux operator is a matrix 2 by 2. So we introduced notations A, B, C of Z and minus A of Z. It is traceless. And its characteristic polynomial L of Z of lambda, which is the determinant of L of Z minus lambda identity matrix, is quite simple in this case. So it is lambda square. It has not the linear term in lambda due to the traceless, due to the Lux matrix is traceless, and plus the determinant of L of Z, and it is lambda square minus A square of Z minus B of Z and C of Z. And one of your home tasks was to understand which coefficients of this expression are dynamical Hamiltonians, and each of them are Casimir functions. So they are not dynamical. They commute with all dynamical variables, so they do not define any dynamics. But in this expression itself, there is some geometrical meaning. So we interpret it as an algebraic curve in C2. But so, if I'm right, we have to consider what is called the rational surface, which is the projectivization of the linear bundle of degree 2 on a rational curve, but it is not principal just now. So we consider this as an equation of an algebraic curve. It is a hyperelliptic curve of high genus if n is greater than 3. It is, or yes, then if it is bigger than 3, that it is a curve of high genus. It is not a rational curve, so there is all the stuff of algebraic geometry on this curve, and a significant science of this algebraic geometry is the construction of separated variables. So we introduce points. So let's define sigma. It is the curve of points such that this is P of Z lambda so it is a curve defined by this equation in C2, and we introduce points Pi on this curve, which is defined by the following variables. Pi is the point given by Zi and lambda I. And there Zi is the 0 of C of Z, and lambda I is A of Zi. So you see, if Zi is the 0 of C of Z, then lambda I equal to A of Z. So if we substitute A of Zi instead of lambda, and we take the value Z equals Zi, then the polynomial equation fulfills. And this is really point on the curve. But moreover, these variables are, so they have demonstrated the lemma that I lambda I, all this set of variables, is a Poisson canonical variables on Poisson canonical variables. It means that Zi lambda j is delta ij, Zj lambda I lambda j 0. And due to this fact, the canonical transformation from this set of variables to the action angle variables is reduced to the two-dimensional problem. So I demonstrated that the canonical transformation from Zi Z1 Zdi which defines the transformation from the variable Zi lambda I to the variables I, j, phi j, the action angle variables for the model. This generating function of this canonical transformation can be decomposed into the sum of one variable functions, such that each of these functions solve such that S of Z I satisfies the following equation: P of Z ds over dz. So I would like to write its dependence also on Hamiltonians, which are the coefficients of this function. So they are plugged into this formula. So it is the following formula. So it is a differential equation of the second order on lambda. So it's a differential operator of second order, and so this is the small s, and this fact demonstrates the the reduction of the problem, of the dynamical problem, to the small order.
Did we claim it's Liouville?
Yes, it is a Liouville integrable, but moreover, there is such a simplification in describing the problem. So we reduced the description of the behavior of all this system to the two-dimensional system. But these coordinates are extremely non-trivial. They're not trivial inside the initial phase space. So you see, these are some points on the curve. They are not related with the spin variables. So the separation of variables is not in terms of these copies of spin variables. Okay. So this was the main statement of our last lecture, and now we go to another subject which has the same status. So it is always present in integrable systems, but there is not such a theorem that you see here there is a method to separate variables to reduce the problem to the two-dimensional one, and it is related to some algebraic curve which is related with the Lax representation. So it's a spectral curve. It's a curve which describes the spectral properties of the Lax operator. And so this point, in fact, it describes a section of some bundle on this curve. So it's a divisor of points. It describes the fiber bundle, linear bundle on this curve. So in terms of such algebraic geometrical terms, one could solve the system, and it is quite general in the theory of integrable systems. But as I said, it is not a theorem. It is some heuristic phenomenon, and what I would like to talk about today has the same nature. So it's a phenomenon. It is always present in integrable system, but there is not such a theorem. And it is called a Bihamiltonian structure. So let us proceed to this property. So first of all, we need a notion of compatible Poisson structures. Two brackets, two Poisson brackets are compatible Poisson brackets if both are Poisson structures and a generic linear combination of them is also a Poisson structure. Okay, so what is non-trivial in if we ask to be a Poisson structure for this linear combination? So the skew symmetry is obvious because it's a linear combination of skew symmetric operation, but the Poisson, so the Leibniz rule is obvious because it's just a linear combination of two operations which are differentiations. But the Jacobi identity is non-trivial, and that's why it's a condition. It's a non-trivial condition on two bivectors. Lemma. Let us define by P1 and P2 the corresponding Poisson bivectors are bivectors corresponding to brackets the brackets are compatible if and only if this Houghton bracket of this bivectors is trivial, and so this Houghton bracket, I suppose we discussed it. So it's an extension of the commutator of vector fields to the graded algebra of polyvector fields. But let us remind the exact form in coordinates of the Houghton bracket. So we written such an equation just for one bivector, that it is equivalent to the following sum: P I S D P G K ds. Sorry, dxs p ks dp ij dxs. And so the condition that two Poisson bivectors commute with respect to the sl₂-Gaudin bracket is equivalent to the following condition. 1. Okay. So lemma says that two such brackets are compatible in our sense if such condition fulfills. Is it obvious, or you prefer me to demonstrate it? So this is known for us. So we discussed it at the beginning of our course, that a Poisson bivector satisfies the sl₂-Gaudin square equal to 0, which is equivalent to the Jacobi identity if this condition is satisfied. So now I ask that the linear combination of such bivectors satisfy this bracket. So we need to plug the sum, the linear combination of bivectors, into this condition, So let me write it schematically. Maybe it will be evident. I'd like to write lambda p1 mu p2 1 p2 sl₂ bracket, and so lambda and mu are constant in this bracket. Is the extension of commutator of vector fields, so there is some differentiation, and the constant doesn't interact with this differentiation. So this is linear with respect to linear combinations with constant coefficients. So it is lambda square p1 plus mu square p2 plus 2 lambda mu p1 p2. So, and we know that it is 0 for all values of lambda and mu. These are zeros because we have chosen a Poisson bivector. So these parts are zeros because pi I are Poisson bivectors. And now we ask that this is 0, so it means that this condition fulfills. And if we just expand this condition and plug in each place as the linear combination of pi1 and pi2, we will get this middle term. Term with coefficients of pi1 and pi2. It will be the expression of such type. Okay, so I suppose you need an example. So let L as before will be the the Lax operator of the Lie algebra GLM. And we know that its standard Poisson structure is given by P L2. So this is the standard Poisson-Lie structure on GLN. P is just the transposition, L2 is, you remember, it is 1L. So I'd like to consider another Poisson structure written in the same form, but with the constant matrix. Here C is a constant matrix. Let us realize when such an expression defines a Poisson structure. So you see it is different from this one. Here, in this case, EIJ, KL is a known formula which we used. JK minus KJ delta IL. In this case, it is just constant. So EIJ with EKL are some constant. I don't know how to write them. AIJKL, just constant. What is needed for such an expression to define the Poisson structure? What do you think?
You mean what conditions?
What are the conditions for this set of numbers that this expression define the Poisson structure on on the same space? Only skew symmetry. The Jacobian identity is automatic, because if you consider the third commutators, they are all zeros. Okay, so if you consider EIJ, EKL, EMN, it is always zero because these are constants. So the only thing to ask is the skew symmetry of this matrix. So we only need that AIJKL is equal minus AKLIJ. That's all. If you have such a matrix, this is the Poisson bracket. Let us understand what happens. I claim that it is automatically true for any matrix C. That it will be a lemma. And let us distinguish between this Poisson bracket. It will be first, and this will be the zero Poisson bracket because it is homogeneous of degree 0. So my statement is that L0 is always Poisson structure. Always mean for all C in matrices n by n. So we need to demonstrate this property ijkl is equal to minus akl j. This is equivalent to the following expression. So it is equivalent to exchanging the components in this Poisson bracket, and I will describe it by matrix operations. So it is equivalent to the following, that P12 L0 P12 is equal to minus L. What do you think? Do you agree? 0. Okay. Let us write it. L0 P12. It is P12. And now commutator P12, C2, P12. And this is, so now I expand the commutator and I will omit indices, so it's always P. P, C2, P minus P, C2, P. It is C2P minus PC2, so it is minus PC2, and it is minus LL. So I demonstrated that the zero bracket is also a Poisson bracket. So next statement will be that they are compatible. One are compatible. How to demonstrate? So what to demonstrate? So I will. So you see, in fact, in this combination of parameters, the only point of the projective line is important. So if we multiply Poisson bivector by a number, by constant, nothing changes. So it is principally the same. So I will demonstrate that 1 plus lambda 0 is also a Poisson bivector, a Poisson structure. Let us demonstrate that it is a Poisson and it means that we consider lambda 0, lambda 10. So I will introduce the following. It's not quite good. Okay, so it is the linear combination of such two. Okay, and what does it mean? Lambda, it is the commutator of P with lambda C. Okay. Now let me introduce new coordinates. It will be L2 tilde. So you see, L is just a matrix, with values from our Poisson the algebra, and I change the variables just in a just a shift of the beginning point. So now L2 ij, it is Eij plus Cij. Okay. And now I would like to write the Poisson bivector operation in terms of this new variable, and I'd like to write such a Poisson bracket, and by linearity it is L plus C lambda, I'm sorry, plus, and this C is just a constant, so it commutes with everything, so it is equal to L lambda, and by this definition it is just P L tilde. Okay. And such coordinates. So you see, we have just introduced another coordinates on another linear generators of the same Poisson algebra. In such coordinates, the bracket has the same form as the bracket 1 with the index 1. But for this bracket we know that it is Poisson. Okay? And obviously it is closely related to the so-called argument shift method. Argument shift method, and we will discuss it in a few minutes. Okay, so I demonstrated that my structure has examples. But now I would like to demonstrate an important property of such a structure. Let us demonstrate another lemma. So suppose are compatible denote by lambda its linear combination is a generic bracket from the pencil so this set of linear combinations of two structures is called the pencil structures, so it's quite general idea in algebraic geometry to consider some linear systems of objects. And C1 of lambda and C2 of lambda are Casimir elements with respect to this generic Poisson bracket. Are Casimir elements and have expansions Ci lambda Ci let me use the most simple situation, lambda 0 plus Ci1 lambda 1, etc. Then Cij Ckl commute for all lambda. So have you written? Can we discuss a little bit the meaning of this statement? So the principal thing is that even you have one central element for this generic Poisson structure, it could depend on lambda. And if we have just one central element, all the coefficients in this expansion commute between themselves. So they produce an evolutive family. So it's an origin of some integrable system, just from the center of the generic Poisson structure here. We will discuss it in the example. So, okay, we'll proceed slowly. Firstly, let me demonstrate this statement. So let C1 of lambda so C1 and C2 are Casimir element for the generic Poisson structure, for the Poisson structure with the index lambda. Let me calculate the Poisson bracket with different values of this parameter at the point lambda and at a point mu. It is always 0. So this bracket is 0 because C1 at a point lambda is the central element with respect to the lambda bracket. So it doesn't depend on the second argument. So, and this is 0 because C2 at the point mu is the central element for the bracket mu. But now what we have that C1 lambda, C2 mu, plus lambda, this is 1, C1 lambda, C2 mu is equal 0. And we also have plus mu. For lambda not equal mu, we have that both brackets are 0, C1 lambda, C2 mu, 1 equals 0, lambda, C2 mu, 2 is equal to 0. Okay, so it means that 1 lambda C2 mu to all brackets in this family. And now we have to expand to substitute this expansion to this formula. It is the sum of over k c I over j lambda j sum over L ck L mu L nu. It is the sum over j and L Cij ckl nu lambda j mu L. So it's series which is 0. So all the coefficients of this series should be 0. Let us talk a little bit about the argument shift method. Historically, it arose in the context of generalization of the Euler top. Do you remember what is the Euler top? So it is described on in terms of the angular momentum of a rigid body in such a form. So it's an angular velocity, this is an angular momentum, and it is the system describes the rotation of the rigid body with a fixed point. And there is some simplification if we write it in the coordinate system of inertia tensor of the body. We can introduce the diagonal matrix. So it is important that it is symmetric, and in some coordinate system it will be just diagonal, and in this case, so it's an inertia shear tensor, and in this case G is equal just I multiplied by omega. So, and you see that the system is quite of the lax form. So it can be interpreted as a lax representation. We discussed it, so if I don't remember, please consult in the previous lectures. Monakov proposed to generalize this system to other groups. So generalized this system to other ranks. So one could understand that this vector is an element of SO3, and G also an element of SO3. Then this is the commutator in SO3. The vector product in R3 represents the commutator in SO3. And E is just some endomorphism in SO3, so it acts like this. So Monakov generalized this system to the following. So now we consider the rank generic. G is SON. So he considered I of the special kind. So first of all, in this case, J, I will write in my notation, and omega are element of SON. And I is also an element, no, it's a symmetric matrix. It's an element of symmetric matrix N. So it's a symmetric matrix N by N. And Monakov described such a system that J is I omega plus omega I for the symmetric matrix of dimension N. So first of all, let us understand that this is again an element of SON. So it corresponds to some endomorphism on the linear space of the Lie algebra. So J transposed is I transposed. I'm sorry. It is omega transposed I transposed plus I transposed omega transposed, and here omega is skew-symmetric and I is symmetric, and that's why it is just minus omega I minus I omega, and this is minus J. So it's a skew-symmetric matrix. The generalized equation, top equation, can be expressed just in terms of omega, like in this case, but it is a little bit different. So it is I omega dot plus omega dot I, and it is equal to omega dot I omega plus omega I, the commutator with omega, and this is, if I remember, I omega square commutator. So evidently, ik, which are traces of j, k, are integrals of motion. And moreover, they are in involution. But in this case, the dimension of the phase space is bigger. It is n square approximately n square over 2. So n spectral invariants, like in many other cases, are absolutely not sufficient for the integrability. Monakov found that this system can be written in a generalized form, dt j plus I square lambda okay. And he understood that you see, we can introduce the Lax operator depending on a parameter. And it is also the Lax equation for this Lax operator, but which depend on the parameter. And this will imply that the traces of j square lambda k are integrals of motion. And these are function on lambda. So if we expand them on lambda, we will get all the necessary number of integrals in involution. Monakov demonstrated that all coefficients in lambda of trace ik of lambda are integrals in involution. And he demonstrated also the sufficient condition that the number of such coefficients which are independent is just the necessary number for the Liouville integrability of this system. So we will discuss a little bit more general application of this method, which is the argument shift method in SLN case. But starting from this work, people understood that it is good to look for some dependence on parameter, and it appears on the level of Poisson bracket and on the level of functions in involution. So argument shift method method in SLN and JLN. So in the subject there is some conflict of authors. So Monakov started to introduce this method for SON, and after that Mishchenko and Fomenko introduced it for all semi-simple Lie algebras. So there is some conflict between these groups, but and very often it is called the Mishchenko-Fomenko method, but you see the story is richer and more interesting than conflicts.
What time of that?
80s. 80s, yes. So I think that Mishchenko known additional integrals. So you remember for this generalized top on SON, the spectral invariants, just the traces of powers of the Lux operator, are not sufficient for integrability. So one needs some additional. And if I know well, Mishchenko found some additional Hamiltonians for small for order 4. And then Monakov found them all just by shifting the Lux operator. And just after that, Mishchenko and Fomenko have written the paper about this method for all semi-simple Lie algebras. Okay. We'll discuss it in a very simple example, simpler than the orthogonal case, and it is the following statement. Let L of Z be L Z plus matrix C. This is the GLN Lux matrix. This is a generic matrix. Okay, but now it depends on parameter Z. And it means that so you understand that L of Z now it is a matrix Eij divided by Z plus Cij. So this is the constant, and this is the generator of our Poisson algebra. My statement is the following: that if we consider, I prefer the characteristic polynomial. If we consider the determinant of L of Z minus lambda E, and I expand it in Z and lambda. So, okay, it is the sum of lambda E, and here it is the sum of E from 0 to N. Now it is the sum G to 0 to I to N minus I. And this is 1 I Ij Z power J. Maybe from 1. No, from 0. Okay. So this is the matrix which has the pole of the first order, and then I consider its characteristic polynomial. So it will be the sum of. So firstly, I expand it on lambda. It is the sum from 0 to n, and the coefficient at lambda I is the sum of minors of degree n minus I, and these minors are rational functions with the order of pole not greater than n minus I. Okay? Theorem. Ij, I, k, L commute with respect to the Poisson bracket we are considering. So, and this is the application of our lemma. So it is demonstrated. It is demonstrated applying the lemma which was here on the involutive family coming from the center of the generic Poisson bracket from the pencil. Pencil of compatible Poisson structures. How it follows? Obviously, I have to calculate the Poisson bracket. So that lambda E and this is over z square L because all the rest is composed by constants. But I'd like to I have too much parameters. Let me consider just this bracket L of z. Just let me multiply by z and calculate such a bracket. This is L by L. I will denote it by L prime, L tilde, and this is P L2, and this is P L2 tilde minus ZC2. This is P L2 tilde minus Z P C2. Sorry?
1 over z square.
1?
1 over z square, that's coefficient. We need to add it.
It's plus. This here.
I mean, you said equal. We should rewrite that coefficient. No, on up.
Here. Here.
I mean, we should add 4.
No. Here.
Yes, we had those
L of z by definition is L of z plus C.
Yes.
So if you write it here, L of z plus C, L of z plus C, the only non-trivial bracket is between L. 1 over z square L by L. No, it's, I think it's correct. But now I have changed a little the notation, so now I introduce such a linear combination, but it differs from this just by multiplication by z. And this is better because you see it's a sum of two it's a sum of two Poisson brackets. We have demonstrated that both of this expression describe the Poisson bracket and they are compatible. Okay. So now if we find the central element of this bracket, we will be able to expand it on the parameter and to consider its coefficients and just a moment. Okay. So now we know that the central element for this bracket, you see, it is just L by L. The central element of this bracket are the center is generated by traces of LK. But so we know the center of this bracket, but in terms of L prime, it will be these elements can be expressed of L tilde so these are traces of L tilde minus Z C K okay, and moreover we can, so it is equivalent to consider the coefficients of the determinant of L tilde ZC minus lambda, and by this trick it is principally the same thing as it was manifested in the theorem. Let's make the break before the seminar part, and we will return to the statement else after the break.